This is Sahan Purasan, and I'm going to present you my work titled as Strain Rate Sensitivity of Electrically Modified Carbon Epoxy Composites Under Dynamic Compressive Loading. So the structure of the work includes the motivation and the projects that we are doing with our partners, the material of the study, the experimental procedures, and the results, conclusion, and the references. Increasing the usage of polymeric composites on the aircraft structures provide benefits in terms of high specific stiffness and strength, but there are some drawbacks. One of them is that the polymeric composites are known to be weak conductors, which increase the vulnerability of the aircraft to lightning strike damage. Aircrafts are estimated to be targeted to one strike roughly between 1,000 to 10,000 hours of flight. And this means for an airliner this corresponds to one strike per year. This can be a direct or indirect effect. In terms of direct effect, it could cause embrittlement, resin evaporation, delamination, and even the ignition of a fuel vapor. And in case of indirect effect would be the damage to the onboard equipment. For decades, aircraft fuselages are made of metallic material like aluminum, which could easily conduct away the currents and need less modifications to cope with lightning. But obviously by increasing the incorporation of composite in the main structures, new solutions need to be proposed. One of them is the commercialized solution by incorporating the metal mesh on the outer skin of the fuselage. And the other one could be the metallized fibers, which by covering the substrate of the fibers with the conductive metals like nickel or copper. Or it could be the nanofillers by incorporating the carbon nanotubes or graphene in the resin, or incorporation of metallic nanowires. So to address this issue, Nanopole project has been started, which is the joint project between Avic Composite Center from China and P.M.G.P from Portugal. The goal of the project is to develop a multifunctional composite material by interleaving silver-loaded conductive wales into a composite laminate, and therefore it is hoped to increase the electrical conductivity as well as the mechanical properties. So the material has been developed by Avic Composite Center, and P.M.G.P is responsible for mechanical and electrical characterization of this material on the various loading rates, loading types, and configurations. So the base material of this study is epoxy resin-based pre-preg reinforced with carbon fibers, which we call it as a reference material. And then the other hand, we have modified material, which is basically the same material by interleaving a layer of silver nanoparticles within this material. The configuration is unidirectional, and these experiments will be covering only compressive loading within different strain rates. So this study will cover the compressive behavior of this material under dynamic and static loading condition. In the case of static loading regime, we have a standard test procedure following exactly the ISO standard, and we call it a standard experiments. And then we have non-standard tests, which are using the test fixtures compatible with the dynamic instrument. The goal was to study the size effect and also to see the difference between the test fixtures. So the dynamic experiments were carried out using Smith-Hopkinson pressure bar. We particularly designed this instrument to carry out the composite specimens. So we chose titanium pressure bars with the diameter of 16 in order to have the right impedance mismatch between the carbon epoxy composites and the pressure bars. So the lengths are also designed accordingly, and we chose steel striker with a length of 800 millimeters to have enough loading pulse to have the pulse duration of 300 and 350 microseconds. And for the data acquisition, we use PC oscilloscope in order to record the signals, namely incident, transmitted, and reflected pulses from Hopkinson bar. And we also use the Photron Mini AX200 equipped with the Nikon 60mm lens in order to monitor the specimen impact under the impact loading. So the sample geometries used in dynamic experiments were exactly the same as non-standard static test. You can see the overall geometry of the specimen. And the fixture used to adapted to Hopkinson bar was designed by Blockle et al. You have the reference here, and you can see the overall view of the setup. Basically, we have our flat rectangular test coupon, which was glued into these two steel adapters. We use a special setup for making sure that the specimen is perfectly aligned. And the assembly was then cured based on the instruction of the supplier, and then we had two mechanical clampings and bounded with the strain gauge to directly monitor the strain value. Then we add the Teflon bushings and the steel tube to prevent misalignment. But before that, we performed several preliminary experiments using glass epoxy composite material to confirm the validity of the experiment. And you can see the post-failure of the specimen subjected to an impact of 7 meters per second. And over here you can see the record from the high-speed camera and also from the cross-section, which actually confirms the validity of the experiments, and we are sure that the failure occurs within the first stress pulse. Here you can see the stress strain behavior of both material configurations performed based on the ISO standard. And in the first glance, you can notice that there is a notable decline in the stiffness value of the modified materials. And over here in the right, we have percent bending as a function of longitudinal strain. And as you can see, the bending behavior appears to be mostly within the plus minus 20%, except for two experiments that are slightly exceeding these limits. And in the case of non-standard compression test using the fixture compatible with the Hopkinson bar, we have the same type of behavior for both material configurations. Again, we can see a notable decline in the stiffness values of the modified specimens, while also we can also see a 20% decline in the ultimate strengths of the specimens, modified specimens. And over here in the right again, we have percent bending as a function of strain, showing a deviation ranging between the plus minus 20%. And finally, we have the overall comparison between the two test fixtures, showing the reliability of this new fixture. The output from split Hopkinson bar analysis are plotted for two material configurations, and we use one-dimensional wave theory to calculate the compressive stress value of the specimens, and we also use the locally bounded strain gauges to calculate the strain value, despite the fact that we could have used it with the one-dimensional analysis by using the reflected signal. And also, as you can see, the profile of the incident pulse, we use the rubber pulse shaper to generate a sort of like ramped triangular incident pulse, which is an ideal shape for testing the composite materials and also brittle materials in general, which generates constant strain rate. You can see the test coupon before and after subjecting to the compressive loading at a velocity of 6.5 meters per second. And over here, we have the dynamic compressive behavior of the samples, and as you can see, they're quite rate sensitive and demonstrating an increase in the ultimate strength and failure strain values. At high loading rate, the compressive strength increases by 62% for modified and roughly around 93% for reference materials. But despite that, loading rate was found to be not influencing the elastic modulus of the material. And again, similar to the static results, modification of these materials appears to reduce the elastic modulus of the material. And here we use the high-speed camera at the 160,000 frames per second to monitor the failure initiation and propagation of the specimen subjected to the impact within the duration of 320 microseconds. And as you can see, the sample is showing a valid failure within the gauge section by splitting along the fiber orientation within the first stress pulse. This confirms the developed testing apparatus as well as the test fixture for dynamic compression experiments of the composites laminates. So in conclusion, we developed a compressive version of split Hopkinson bar to characterize the composite materials, and we found that the in-plane compressive behavior of the carbon epoxy composites are quite rate dependent, while the elastic modulus of the material appears to be not affected by the loading rate. And also the electrical modification of this material appears to lower the stiffness value of the carbon epoxy composite regardless of the loading rate being subjected to. And finally, no size effect was observed under static loading condition. And thank you for your attention, and I will be happy to reply to your questions.